The starting functional group in this example is an iminium ion. This iminium ion, upon hydrolysis, gives a ketone where an oxygen has replaced the nitrogen. So that would be cyclohexanone. And the amine that is generated here, get my ring size right, would be this one here. The overall charge balance of this reaction would require that if I have a plus charge on the left side of this equation, then I need a plus charge on the right side of this equation. So I could say NH2 plus as the ammonium ion. And on the left side of this equation, I need a source of that oxygen. So that's my water molecule. This is a hydrolysis reaction. This reaction can be done under acid conditions or no catalyst, which is the equivalent of base conditions. Okay, so let's go ahead and start under conditions where acid is present. This iminium ion is already an active electrophile, and so the water can attack directly. If we have an acid as the catalyst here, we're actually going to be starting with the conjugate base of the acid for the reaction in this direction because we started with a plus charge on our reactant. So I'm just going to use a water molecule here. Here's my water molecule. The water is going to act as a very weak base, the conjugate base of a strong acid. And so here's that strong acid that is generated when I use water as a base. The next step, if I'm aiming towards explaining getting rid of the nitrogen on this structure, is that the nitrogen needs to get protonated. And so the nitrogen protonation looks like this, giving us a plus charge on the nitrogen. That nitrogen is now available to get kicked out. So here I am kicking it out. It's nitrogen neutral. And since I've balanced my equation by putting an ammonium ion there, I'm going to go ahead and use that as the base in this step. Ooh, that's an ugly looking bond. Let's make that a little bit cleaner. I'll redraw the whole ring. There we go. I'm gonna check, zoom out here, make sure I covered everything. If I'm labeling this as the acid conditions, I'm just going to point out that here is the acid and its conjugate base. So I'll put those labels in. This is You'll notice that since the starting material had a positive charge in it, our labeling for what counts as an acid, as acid conditions, feels a little bit backwards. Okay, speaking of backwards, let's do the reaction in the reverse direction. So we're going to come over here at the end, and we have a ketone. Here's the ketone. This ketone can react with the ammonium ion. That proton transfer serves two purposes. It makes the carbonyl more electrophilic, and it makes the nitrogen a valid nucleophile, because now the nitrogen has a lone pair. That nitrogen can then attack the carbonyl carbon. The nitrogen should still have a positive charge now. In the next step, we need a base, a very weak base, the conjugate base of a strong acid, because we're thinking about this being acid type conditions. So here it is, deprotonating the nitrogen. And that gets us our neutral hemiaminal structure. Which I had forgotten to label in the above scheme, but it's the same one. I'm checking as I go that all my intermediates are lining up. The principle of microscopic reversibility here, helping me to make sure my mechanisms include everything. Okay, the next step, I used water as a very weak base, and now I'm going to use its conjugate acid as a strong acid. Under acid type conditions, before I can kick out an oxygen, I'm going to protonate. That can now get kicked out as a neutral water molecule. So here's water leaving. And that gives me the iminium ion that I started with. Again, let's highlight the catalysis here that's happening. We're using a water molecule and a strong acid as the conjugate acid of that. And we can compare that now to conditions where we don't have a catalyst. Under conditions where we don't have a catalyst, the iminium ion is going to need to react with a hydroxide ion. So it might feel more normal to call this base conditions. Remember that since we're starting from a charged intermediate, the labeling seems a little bit strange. Okay, so here's the iminium ion. Ooh, let's try that ring size again. Double bond, 6-membered ring. So my hydroxide ion can attack that gives the neutral hemiaminal structure directly. The hemiaminal can get protonated at nitrogen by water, which was the conjugate acid of the strong base that we used. It's now ready to act as a leaving group, but under conditions where I have hydroxide present, I'm not ready to kick it out yet, because if I kicked it out right now, I would end up with an oxygen that has a plus charge in the presence of oxygen with minus charges. We're trying to avoid that in our mechanisms. So I'm going to take this OH group and I'm going to draw it out more explicitly so I can show its deprotonation. Here's the alkoxide, the negative charge, that's going to come help kick out the nitrogen. So I have a neutral nitrogen, and I have a ketone. And that's it. In the reverse direction, let's zoom back in here. In the reverse direction, if I start with the ketone, and the amine, the amine is a good enough nucleophile to go ahead and just attack the carbonyl directly. That creates this structure that has charges on both the nitrogen and the oxygen. If I'm going to be getting rid of that oxygen as a leaving group, I need to protonate it. Here it is getting protonated by a very weak acid, water. Before the nitrogen can help to kick out the hydroxide, it needs to get deprotonated. So here's the hydroxide ion, the conjugate base of the very weak acid that I just used. The hydroxide can deprotonate here. That nitrogen lone pair is now available. This is the hemiaminal structure. That nitrogen lone pair is now available to kick out hydroxide. Which gets back to the iminium ion that this question started with. Just zooming way out so we can compare here. Same iminium ion.